So thank you very much. Thank you everyone for being here. So my name is Deb, and on behalf of my team today, I would like to present our solution to the problem of how to design a machine learning system to predict
Yeah, I'm sorry. I had to share your presentation with the online participants. Really tough. Yes. So, yeah. Okay, go ahead.
hold this.
Yes.
Okay. So on behalf of my team, I would like to present our solution to the problem of how to design machine learning systems to predict the incoming requests to the data port or ICR data photo. So before I start, I would like to thanks our mentors to make it happen. Okay. So precisely what is the problem? So imagine you are a practitioner and you go to that data center, you have that portal, and you looking for some data. You fill some requirement for the data, and you send a request. So and you wait for about second, a couple of seconds, minutes, and hours. The point is you don't know about the processing time of the request. So that and also from the server side, most of the server look at the request and it's look at the number of the field and like have a rule-based system to try uh, to make some prediction on the computation cost. So it is like fixed rules, not really based on the data. So that highlight the need to make a system that could that driving system that could make a good prediction on how long the preset will take. And for the server side, it could be used as a proxy for the computational cost to the system. This would enhance the user experience from the user side and enhances resource allocation, better route forecasting. So the like other so the first thing is we have a lot of data, so we can use machine learning model. The pattern is very simple. It's just basically us coming in. So we have a bunch of data. So we train a model, a machine learning model, and when the data come in, we try to normalize the data request. We do some feature engineering to make it numerical value, so it can be digested by a machine learning model. And the end, the model spit out some prediction. So the key component here is that we have first layer. So here is our solution. It is based on a 4-layer picture. So first, when the request come in, on the schema handler layer will look at the data and try to make it normalize as much as possible. And then come to the feature engineering. So it will try to make uh, the the request as a numerical value. So for example, when you select some category, it will bring it to issue Antoine encoding or multi-label by binary relation for for the such kind of value. And for example, for we have some numerical arrays, we can do some separation with that. And at the end, we have after that we have machine learning model attributes with high parameter optimization. It's already in tune, and it will spit out some value. And the BIB packages has a podcast API program. So at the end, we have three high-tank endpoint, definitely for training. Second one, arguing and training, and the last one is to inference. So what we have done is feature engineering. So we build a multi-type equity pipeline with diverse data set. For example, when you see in here, it is basically an example of the request. and you have like this is I think it's a request what we can global data set, can global atmospheric data set, and for example for the first variety over ozone nitrogen dioxide, and we can according to 0 and 1 in value. For other type such as the um uh, time is 0, 6, 12 hours, and 18 hours, we can combine it into just we just count the variable. And for commenting, it's also have some layer for like fast access and slow access. So it's also have to take into account the data is produced. Like if we request that more than 30 days before, it could involve slow access data. So it also had to be one kind of feature that put into this kind of request. After that, we have now we have after the feature engineering, we have XGBoost model that try variable kind of hyperparameter, and again we have a IQ model, and later we have a layer is called model validation. We look into the distribution with prediction and try to iterate on our training. So this is what we have achieved with complete the training pipeline. We tried and evaluate with the 18 key data set. Um, uh, would have a hyperparameter tuning with with optimization, and we evaluate with three matrices, and have later with some valid visualization tools for um further assess the model performance. So here is kind of we are present here for the four most used dataset. Like for the first dataset, we have the 40 dataset we put it to appendix, depending on interested. So for example, here we see that the FIPs is kind of to to measure the um uh mean absolute percentage errors, is to try to say how much as a percentage of PDA can be brush shows, and it's around 30%. Yeah, each model. Except for the CAM is a bit high, and we look at the IMSDs, which is 900 seconds, or we even look further into this one when we analyze the result. For example, here is um, the reanalysis error of a single levels. So in the left, we have the original plot is which basically we just compare the predicted value and actual iteration. And the right is we measure the deviation relative to the graph truth. So basically, it is a graph truth minus prediction over the graph truth. And we, for example, on the left side, we see the residual plot, and there was always some. For example, when you look into the okay, uh, okay. So when we look into this um graph, we see that for example, there was always have a value around 120 or 230, 247, and um for some reason is appeared that in the training data set, and it could signify the timeout request. So it's kind of a kind of data filter. Later, the second observation, we see that uh, there was some kind of request that we had the predicted values like constant. However, in the actual duration, it is ranged from I don't know 2, 3, 4 seconds up to 160 seconds something. And is it kind of what was the very observation we see on the dataset is that because in our training we already use this user request data. Um, so but if we don't take into account the server side information, and actually when we do this experiment with with this kind of data set, we send the set uh, request with some changes to try to avoid the cache. And we see that okay, we even with a kind of same side request, the system split out different duration, and it could range like uh, uh, at in deviation around 20 seconds. So this we think that this kind of range that is unavoidable because uh, even with the same input, the system spit out different output. Um, uh, Next one is for the pressure level. This is also the same problem uh, with this. There was always some value here in the second. Um, and there was always uh, trade with the constant each character duration is by. Next, we have global the time data set, and then another observation is that so before we see that the CAM global data set is around 900 second in RMSEs. One of the problem of this one is that for this particular data set, we see that for some value is can go up to 100,000 second, and even that model has okay for the smaller value, but if it's make a wrong like a wrong prediction on this such scale, it can really bias the errors. And on the residual plot, you see that there will be a small bump in this on the left side. Uh, so I think it's it compared to errors. Yes, and at the end it sees can throw up air quality. But this in this channel says the performance kind of okay. It means the MAE is around maybe 1 or 2 seconds. But it's also evolving to the scale the request is around only up to 100 seconds. So here is FAI layers. So with basically we have 3 layers like prediction layer, training layer, and hyperparameter tuning layer. And here this is a small visualization of the IK layers. So here's an example of what it's a what we should use in real time. Is then people make a request, and this is here's okay. So here so we see that when the user make a request with this request ID like that, it take around 2 minutes 50 seconds, and our model result in around 150 seconds. Okay, so here is so during our development of model, there was some challenge we identified. The first one is the data heterogeneity. So we see that in our picture there was one error is post schema handler, and for each data set is kind of different. So we had to implement it differently for each data set. So for that feature, we already take into account the user side data, and we then take into account the server side data. So it's kind of one feature about auto that is lightweight. We already take into account the incoming request, but that it could bring in the incomplete information to predict to make a free side prediction. Another problem is a temporal creep. So when we try with train model in one day and training the value in the next day, you see that for certain days in the week, there was some change in the partners of the errors, and later is a caching effect. So even though our data is trained on the cache data on queried by our mentor, um, sometimes there were some caching layer from the data providers that may steal some code causing up caching effects, and that is could reduce actual processing time. Then this is our conclusion. We had make small proof of concept of machine learning approach for 80 dataset. We try with some key among that with some key dataset, and the program had 3 layers, API layers, and it's like a functional prototype, but further uh integrate into the ACM technical system. Thank you.
Thank you very much, Yep. Are there any questions?
I'm just curious. Did you have a look at? Sorry. Yeah. Did you have a look at the volume, trying to estimate the volume of the request instead of the duration?
The void and
Yeah, the data volume.
now for us, I think for the dataset we have this holding the start time, the end time of the request, and then we at the end we only try to predict the processing path as a processing of the inpatient cost.
So you didn't have any information about that because
It will matter protect some work. I'll answer this question. We already have that implemented in the data stores, but it's not really enough. Somehow the users are not really do not really understand what the cost means. And frankly, yes, the cost is a bit more complex than just counting the fields. And a field for one data set doesn't necessarily mean the same effort put into by the data stores as for the next data set. So we are trying to find a uniform way to describe things, and I guess the time that the user needs to wait for the request to produce a result, that is the most important thing to try to predict. So that's kind of the point of the challenge to create a uniform measure.
Question. Just want to stress the fact that the size of a request is not really the principal aspect, because if you have any post-processing in the request, you may end up with a smaller file, but a lot of processing, which takes time. And so the key value is time in this context. Maybe is not the only value that can be mapped to an actual cost, maybe not alone, but the size usually is really misleading because the longest requests are put in terabytes or big hundreds of gigabytes for returning a few kilobytes. So, and that take much longer than a request that just returned the data that was moved.
That is Jonata. He is also one of the mentors of the team. And as we are on it, Achel, would you just also come online? Switch on your. Okay. So yeah. Unfortunately, the mentors couldn't make it. So yeah. Good. Well, there was a question from Moisen.
Yeah, one question I was curious, you also experimented with other machine learning models other than XGBooks?
Yeah. Yes. So we try with LightGBL, try with like app PFN. And then actually push the red recognize reversal. Had also use a tree based one. But at the end, the tree push is always like the best fiction. So at the end, we just use a deeper model. It can, I think in the hyperparameter tuning is also quite often to like drive the model, but for me, our hearing is not really was sharp.
There was another raised hand, or do I? Okay, then thank you very much, Liv, and Chrissy. And